in our airplanes, where they come from, and maybe even dispel a couple of myths, or at least change the way we think about things. So, as I've mentioned before, flying doesn't happen to us, it happens because of us. Our actions have consequences, performance consequences. And so I like pilots to get out of the habit of saying the airplane stalled, or the airplane spun, or the airplane did this or that, or the other thing. No, we made that happen, right? We've all heard stories of people hand-popping something like a champ and it goes and flies away and it doesn't stall or spin. It ran into the trees somewhere. But put the pilot in the cockpit and then other bad things happen. Part of this is based on, I spent last summer thinking about principles in aviation, and a year ago I came up with 9 principles of light airplane flying, the basic tenets. And so there are only 9 of them, but they seem to fall into 3 broad categories: mindset, motion, and mechanics. And we've got optimal learning, risk management, fly the airplane. So none of these are new. I mean, we've all seen or heard of them somewhere along the line. Rolling on pitch, lines and circles, time and distance, action, reaction, stall, flight, energy management. So tonight I'm going to kind of talk about the energy management principle, which is kind of a hot topic right now. And one of the most common phrases that comes out of that is pitch plus power equals performance. Is there anyone who has not heard that at some point in their flying career? You're new, maybe it hasn't come to you yet, but it will. Somebody will say it. It's been said here tonight. Let's talk about the 3 different modes that will kind of relate to energy management as far as we're concerned. There's a driving mode, which most of us didn't get here. There's a gliding mode and there's a flying mode. And in terms of the driving mode, of course, there's a power curve for everything, right? If it's got a motor in it, it's a power curve. And the relationship is power's on the vertical and we've got speed along the horizontal. And there's this somewhat exponential curve. I mean, the faster you want to go, the more and more power you're going to need. And that power grows a lot more rapidly than say, the incremental change in the speed. And one of the things we notice is that in a driving mode, for every 1 speed, there's a certain amount of horsepower required. It's a 1-to-1 thing, right? And can anybody tell me in the context of driving what the green line represents? What is it? Well, it's the power required for constant speed. Since there's a 1-to-1 relationship between the two. If I want to drive at 60, I'm going to need about 36 or 7 horsepower to make that happen, right? On a level road, normal conditions. Are there any things we do in aviation that are in driving mode?
Taxi.
Taxi. What else?
Cruise.
Straight and level
Well,
flight?
cruise is not really driving mode, is it? Because we're not on a surface.
Takeoffs and landings.
The takeoff roll, right, when we're on the runway, and the landing roll. So taxiing is the same as driving mode, okay? And in some cases, we're still trying to invent, I don't know why we're trying to invent flying cars, because we already have flying cars. They're called Cessna 172s. But if we have a flying car, we're going to have to taxi a lot farther to get to the runway. Driving. And so if we want to talk about pitch and power equals performance in that context, it's silly to talk about pitch, right? That has nothing to do with driving mode. Nothing to do with taxi, nothing to do with takeoff, roll, or landing mode. It's all about power gives us performance. All right, so let's look at the gliding mode, and it's kind of a similar shape, but it's sort of inverted from driving mode. But similar thing, we've got on the horizontal, we've got speed, and on the vertical, it's not power because, well, gravity is the power at this point. It's rate of descent. Do we have any glider pilots in here? Okay, so it's kind of somewhat familiar, right, to what you guys are doing. And similar to the driving mode, there's a 1-to-1 relationship here, right? So if I'm going to be gliding at a particular speed, there's going to be some kind of a corresponding cost to do that. And we see that cost in terms of our rate of descent, how fast we're going to come down. And just like driving mode, it's not only 1-to-1, but we can only ever be on the green line. And so, what might we call this green line? So I call it's the altitude burn required for constant speed. Right? This is what it takes for you to glide at a particular speed. Okay, So similar to driving mode from that standpoint, you can only ever be on it, one-to-one relationship. Pitch plus power equals performance. If we're going to talk about that in this context, well, of course, there is no power, right? Either because we cut away from it after paying the tow fee, or the engine stopped producing power for some reason. Usually because the pilot hasn't done the right things regarding fuel. So if we do the right things regarding fuel, we'll probably have power most of the time. So now I'm going to talk about the flying mode, and I'm going to use real numbers, real graphs from a real airplane. And it's that one right there, 6346 Delta, from John Lowry, who put together this computing airplane performance using what he calls a bootstrap approach, where you take an airplane, you can do a couple of test flights with it, collect 9 different parameters, measure 9 different things, and then you know everything about your airplane you ever want to know. Far more accurate than the generic POH information. He ended up writing a book later on called Light Airplane Performance, published by AIAA. So a familiar curve looks pretty much like the glide curve flipped up again, right? So kind of like a Nike swoosh, but same as we've seen in the other 2 modes. Airspeed along the horizontal, in this case we've got the power on the vertical. And this particular configuration, 172, it's at 2,400 pounds, density altitude is 3,000 feet, the flaps are up. So there's always a set of conditions around each of these pictures. And just like we've seen before, if we're going to be on the green line, there's a one-to-one relationship on the green line at a particular speed, in this case 80 knots, and this is all calibrated in this case. It's going to require 60 horsepower. Okay? Can anybody tell me what this green line means? In fact, let's take one step back from that. When we're in flying mode, do we have to always be on the green line? No. We can be over here, can't we? Which is a peculiar thing about flying. It's one of the things that distinguishes it from gliding or driving. Can we be over here? Yeah, sure. So if that's the case, what does it mean to be on the green line in flying mode? We saw what it meant in driving mode. I told you my interpretation, at least in gliding mode. What does it mean when we're on the green line in flying mode?
Level flight.
Yes, the power required for level flight. And let's see where that comes from. Who's read Aerodynamics for Naval Aviators, at least the subsonic part of it? Okay, you probably read the supersonic part too. 1965, items of airplane performance, straight and level flight. Here's a picture, looks kind of similar to what I just had up there in black and white. And power required, level flight performance. Right? Power required for level flight. Now, okay, book came out in 1996. It's passing around the room right now. There's a chapter in there called Energy Management, before energy management was cool in general aviation, at least. There's a picture that looks kind of like the pictures we've been seeing already. And here's what it says. Power required for steady level flight. That's not the same definition as in driving mode, is it? It's not the same definition as it is in gliding mode. And so, if we kind of shoot ahead a little bit, this is the FAA. 2008, their pilot, this is the Pilot's Handbook of Aeronautical Knowledge. The phrase power required appears in there about 30 times. But the clarifying phrase, steady level flight, associated with power required phrase, only appears 6 times. Why is that? Why do we not tell the whole story most of the time here? Well, let's jump forward to the current version. This is the Airplane Flying Handbook, 2021. This one came out with a brand new energy management chapter, because that's in vogue now. 7,500 words in this new chapter. Has anybody read it yet? Yeah, please don't. It kind of sucks. Power required is mentioned 17 times. There's not one single mention of steady level flight attached to that. Why do we do that? Why do we tell people what we're talking about? We got to figure that out. That doesn't make any sense to me. It's the power required for constant altitude. The name of the green curve tells us what we use power for. And yet we're going to sit around and have debates all the time about what we use power for. By definition, it's the power required for constant altitude. But, as we said, we don't have to be on the green curve in flying mode. That's what's so cool about aviation. So, not like driving and gliding modes at all, which is the power required for constant speed or the altitude burn rate required for constant speed. Those two are about speed. This is about altitude. So, if we go back to stick and rudder, they tell us, kind of give us a little bit of insight, the conventional airplane is not a common sense contraption. It's not like driving. It's not even like gliding. It's totally different in a lot of ways. So let's come back here and have a look. Anybody tell me what the red curve is on here?
Power available.
Power available. Where's the power available come from?
Engine.
Is it pedaling a bicycle? Where does it come from?
Engine.
Yeah, it's the power available from the engine. Why don't we say that? Everybody will say, oh, it's the power required and power available. From where, for what, right?
There's a propeller engine combination.
Yeah, so we'll just kind of lump all that together.
Yeah, required.
And so let's call this PAV, that's power available, and PRE is power required. If we look at the difference between the two curves, and we drop that down, and we do that all along here, we can come up with a third kind of curve that we rarely see in general aviation. We'll call it the blue curve. And this is the excess power. This is the power in excess of what's required to be on the green line, on the green curve. Okay? So I have power available, power required, and then power excess. And from here, we can just reinforce everything. If we're on the green line, that's level altitude, constant altitude. What if we're in the blue shaded area? What's happening?
They're climbing.
Yeah, we're climbing. Sure. What if we're in the tan area? What's happening?
Descent.
No, we're not climbing, we're descending. Right? So these are the things we can do in flying mode that we, unless you're Dukes of Hazzard, don't do in driving mode or can do necessarily in gliding mode. And then we break this down even more. I'm not exactly sure why. We talk about this normal command region and somewhere back here, the reverse command region. The controls don't really work in reverse or anything like that. Even in aerobatic flying, they don't work in reverse. Your left foot on the left rudder is still left, so none of that really changes. But anyway, FAA came out with an advisory circular, I think it was dated 1976. The region of normal command may create doubt as the primary control of airspeed and altitude. But if we understand what the curves mean, what their definition is, there really shouldn't be any confusion. And by the way, this advisory circular has never been superseded. So it's still in effect, if you can find it. So let's have a look here. This is going to be, and again, these are the actual curves of that Cessna 172 that I showed you earlier. All of these curves, whenever we look at these kind of pictures, they are snapshots in time for a particular set of conditions. So this is for that same 172. Density altitude is 0, right? So what happens to these curves as we go higher and higher? What happens to the performance of your airplane?
Drops off.
Yeah, it drops off. Well, we can actually show that here, right? In 1,000-foot increments, we can see what happens. Power available goes down, power required goes up, the excess power goes down. And pretty soon, we can't do anything but stay where we are, right? So all of that, all of the stuff we know or we're told about comes from somewhere, and we can actually see it in the math, right? If we want to think of it like that. So let's zero in on the power excess curve here. How do we typically measure the effects of excess power in an airplane? How do we know? How do we know we're accessing excess power? Altimeter goes up, right? But it's, yeah, rate of climb. So we can put a rate of climb scale here. And this is the rate of climb scale for that particular 172 at a 3,000-foot density altitude. Okay? So we'll just put that scale on here. So now we have kind of the filling in some more of the information. Then in this mysterious cloud, I'm going to put a bunch of v-speeds. Because all of the v-speeds we talk about come from somewhere. And a lot of these come from the picture here. And so let's look at a few of them. If we draw horizontal lines that intersect the green arc and the blue arc, we get a couple of key V speeds. One is VE, our maximum endurance speed, the other is VY. So maximum endurance, what does that mean? What does that give us if we fly at that particular speed?
For the longest range.
Yeah, or the longest time, right? It's the lowest fuel burn. How far we go depends on a lot of different things. But it's our maximum time aloft. What about VY? What does that give us? Best rate. So in that case, we can climb to altitude in the least amount of time. So these two numbers, which come from the horizontal, are about time. Time aloft, or time to get there, right? And so, kind of an interesting way to look at it. So now if we do tangent lines that just touch the green and the blue, we get two other key speeds. One Vx, where it meets the blue line, and V best glide, where it meets the green line. What is Vx? What does that give
Angle
us?
of climb.
Best angle of climb. What does best glide give us? Shallowest angle of descent, right? So these two things are related by feet per foot. That's how we can measure it. By an angle. This particular airplane will climb just over 4 degrees, and it'll descend at about just over 5 minutes. Okay? So let's look at a couple of others. Let's look at where the green and the red lines touch each other, where they cross. Two key speeds, V little m. This is the minimum level flight speed. And then we have VH. What is VH? Maximum level flight speed. Can you fly faster than VH? Yes, but
Your descent.
yeah, you can't stay at altitude. Right? You can't. Yeah, right. So it's the maximum level flight speed. So it's everything in between is level flight. We can be on the green curve. Right? So it just came off of the Reno Air Races. What's the objective of Reno Air Race?
Speed,
Speed to do what?
go around pylons.
Go around pylons. It's really about maximizing VH, isn't it? It's to see who can go the fastest in essentially level flight. So how do they do that?
Increase power.
You increase power and you decrease drag to push these curves around and push VH that way. If it was just about seeing who can go the fastest, fastest VNE wins, right? But that's not what the Reno Air Races are about. It's about how fast can you go in level flight. And so you do drag reduction and you do power increases. Right? All right, let's draw two more. These are vertical lines here. VNE, red line, what does that mean?
Never exceed.
Bad things might happen if we go faster than that. So that's a structural limit. So we have a kind of a power plant and prop limitation with the red line. We have a vertical limit out there, structural. What's VS? VS? VS as in Sierra? Stall. That's an aerodynamic limit. So now we're putting limits on where we can operate here. And practically speaking, unless you're flying at really high altitudes, that whole side to the left of the stall speed is unavailable to us. So we can never really get down to the minimum level flight speed because the stall will get in the way first. So let's talk about a go-around, practical situation. So let's say we're in this 172 and we decide to go around. At the instant we decide to go around, we're at 60 knots. And we add full power, so we're on the red line. And everybody knows, well, you pull to go up, right? And if we do pull long enough, hard enough, far enough, what happens? Do we go up? Yeah, we're going to come down, right? It's that houses get smaller than the houses get bigger thing, right? And you can stall the airplane even if you don't do the pullback. If you have it trimmed for power off, it's an elevator trim stall. Anybody ever practice that for any of their ratings? You're supposed to. It's in the advisory circular that's been around since 1991. Somebody in Australia said, oh, you can't stall a Cessna 172 just by letting the trim do it. So what we did was advanced the throttle slowly, but we didn't put any pressure on the rudder or any pressure on the yoke at all. We let the aerodynamics of the trim and the engine effects do what it does. And look, there's a stall right there. Okay?
That's strongly dependent on CG of the airplane.
Yeah, if we had put 2 more people in with us and that case of oil and
Yeah,
all our camping gear, guess what?
I think it's worse. Yeah.
It gets, yeah, it never gets better, right? And so on the go-around, here's the weird thing, which goes back to Wolfgang Langewisch saying that the airplane's not a common sense contraption. If we want to get maximum rate of climb on the go-around, we're going to add power, we're going to push forward. That's weird, isn't it? Pushing forward allows you to climb faster. Totally counterintuitive. But it's exactly consistent with the law that governs. So let's talk about our pitch plus power equals performance. And in terms of pitch, what is pitch control, really? What is the key thing that pitch controls?
Angle of attack.
Angle of attack, right? So let's put that in there. So you have a full panel, you can't put anything else on the panel whatsoever, but you have this brand spanking new angle of attack indicator. Which instrument are you going to replace? Which one are you going to replace?
I think you get rid of rate of climb.
Airspeed.
Yeah, whatever, just replace the airspeed. Because aren't they kind of related? Right? Why do we have airspeed in an airplane? You know, the Wright brothers didn't have airspeed when they did their flying. In fact, they learned to fly laying on their stomachs. We get all hot and bothered that we got to sit in the cockpit, right? Why do we have airspeed indicators in an airplane? Because we want to know how long it's going to take us to get somewhere. That's the only reason. Well, the secondary reason is we can brag about how fast we go. Other than that, who cares? Can you fly an airplane totally by angle of attack? Yeah. You need some other way to figure out how long it's going to take to get there. But, yeah.
And you don't really use airspeed for that anyway.
Right.
I'm supposed
Right.
to go out the window and mark on the map and all that stuff.
Sure. Exactly. It's one way to kind of get us there, right? So, angle of attack, if we want to sort of branch that into a couple of other things that we might use in the airplane, one is airspeed, the other one is G-load, isn't it? Doesn't airspeed and G-load, aren't they surrogates for what's happening with angle of attack? So why don't we put that in there? We'll put V and G, and we'll abbreviate power as P. So speed and G and P give us some kind of performance. And we can actually break this down and be a little bit more specific. Airplanes do 2 things from a performance standpoint. There's climb performance, and from an engineering standpoint, climb can be positive, 0 or negative, right? So if we adopt kind of an engineering point of view about it. And then we have maneuvering performance. So when we talk about pitch plus power equals performance, there's a lot in there, right? But it really boils down to speed, G, and power. So we've been talking about the graphs before were the, let's go back to it, were the V and P diagrams, weren't they? So let's talk about the maneuvering performance next. So this is a 172 in the normal category. The information you see in red is scattered throughout the flying handbook, the POH for the airplane. It's not all in one place. But the cool thing is, we can do the same math that the manufacturer does to make their math show up in the POH. All you need for the flaps up case is to know that 0 bank at 51, and you can calculate all kinds of things from that. Same thing with the flaps down. It's a pretty simple relationship, so we can kind of flesh out a table here. And then, yes.
You can't read the table, what's on it?
Yeah, so these are stall speeds.
Okay.
So if I don't think the laser will point on there. VNE, VA, VFE. These sound familiar? I have to explain what VFE is to anybody? Flap extension speed. Okay. 60-degree bank, 45, 30, 0-degree bank, 2,400 pounds power off, CG aft, things that you'll find in the POH. And we got the flaps up case, and you got the flaps at 30 case. The column on the other side here, this is G load. It's a normal category airplane, it's 3.8 G is the design limit. VFE, the design limit, drops with the flaps down to 3, so those are G load. Well, we can put in a whole bunch of other G loads, just whatever we want to put in, do a little bit of math, put it into Excel, and make a VG diagram for the airplane. So instead of having 4 or 5 points on this, we can have all the points, on the positive G side. And so the red curve is the flaps up case. The yellow curve is the flaps down, flaps 30. Okay? And just like we did before, we can put some key stuff in a cloud. And we can look at a few different things. So let's go to the limits. So I'm going to call that GNE, which is the design limit. We have one up here at the top, 3.8 in the normal category, flaps up. The flaps down, it's going to be less than 3.8. In this particular case, it's 3. Then we have VNE. There's that same limit we had on the earlier diagram. And then that's VFE. Okay? So we got 2 maneuvering envelopes for the same airplane. One flaps up, one flaps down. Let's put some more here. So we have 1G stall speed, VS, with the flaps up. We have the 1G stall speed with the flaps down. What do we know about the 1G stall speed when the flaps are down compared to the 1G stall speed when the flaps are up? What's the relationship?
Should be slower than lower.
The flaps down stall speed is slower. That's why we put flaps on airplanes, right? So we can land slower, but still have margin to stalling the airplane and land shorter. So we don't need 10,000-foot runways here and there. Well, we can see that right here on the picture. That's where it comes from, right here.
Poor air poop doesn't have a chance.
Yeah, so I said most general aviation, well, there's always an exception to the rule, isn't there? And then the curved lines, this is the critical angle of attack. So that's the aerodynamic limit. So we have structural limits on the horizontals and the verticals. We have aerodynamic limit on the curve, right? So we can't really go out of bounds here, at least we shouldn't go out of bounds. And then there's one more thing here, I'm calling it M. M for stall speed multiplier. Anytime there's G, we can relate the G by taking the square root of it, simple math, and I'm going to call that column over there the stall speed multiplier. It's the factor by which the 1G stall speed will change at a different G load. So what's the square root of 4? Anybody remember from school? 2. So if you're pulling 4 Gs, the stall speed is doubled compared to the 1G stall speed. That's all it needs, right?
Say that again?
So if you're pulling 4 Gs, your stall speed at 4 Gs is twice the stall speed of 1G, right? We know stall speed goes up as weight goes up, as G goes up, and it goes down as well in the other direction. So if we go through the red lines, bad things happen. So if we go through the curve, airflow separates from the wing. If we go through the horizontal or the vertical, the wing might separate from the airplane. Go to the red line, something's going to leave the airplane. Your choice of what that's going to be. Who thinks it's easier to recover from a stall in most cases than to bail out of the broken airplane? How many people are wearing parachutes? How many people are flying planes equipped with parachutes? Okay, do I have any serious drivers in here? Or ultralight pilots? And so most of our flying occurs really kind of along that 1G line, that's that gray line there. But here's the interesting thing that we don't really talk about in flying. We have these 2 performance diagrams. We have VP, that's the power curve, we call that.